laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
You have a real treat in store for you this evening. There's a special group of people going to give, I think, just a fantastic demonstration of science. My name is Warren Buck, and I am a professor of physics at Hampton University. And I come and go from Jefferson Lab quite a bit. I have an office here and have been here since '84. I've seen a lot of these science series, and I think this one is a real special one. And I'm so happy to see so many of you here tonight, because it's just a full house, and I think it's going to be really worth it. What we have is a group of people led by Professor Keppel, Cynthia Keppel, who's professor of physics at, assistant professor of physics at Hampton University, and she's a staff scientist here at the Jefferson Lab. And what she's done is put together a team of students, undergraduate students, from Hampton in the form of a club. It's called the Society of Physics Students, SPS Club. It's a national organization, and Hampton University has a chapter, as well as some other universities in the area have chapters. And two students in this particular club are going to demonstrate for you today some of the things that have really made them more and more prominent, certainly in the state and in the country. This is an award-winning group. This group won the 1997 Blake Lilly Award for the SPS. This is a major award that is only given to one group annually. So what you're about to see is something rare, and I'm sure you're going to enjoy it. So without further ado, let me just say Thea Keppel. Is Thea Keppel here, who's the professor? And it's Thea who's really done this, who's organized this, to make this possible. Her PhD is from American University by way of the Stanford Linear Accelerator Facility in Stanford, California. And she's coming out of St. John's College in Annapolis, Maryland, where she got her undergraduate degree. So we're real happy that she's with us right now and at Hampton University and at Jefferson Lab. And the two gentlemen that she's going to be having fun with tonight are Tege. There's Tege over there. And Neil. You'll hear more about these as we go along, but these are two undergraduate students, and you'll see that they're really quite exceptional. So, Thea.
Hi. Just going to tell you that I've renamed the show, actually, for tonight, borrowing from the writer Oscar Wilde. I decided to call it Physics Visible Mysteries, and that's because what you're going to be seeing are a lot of very visual demonstrations of natural phenomena, mysteries which can be explained by physics, and explanations will follow each demonstration. Specifically, what you'll see are demonstrations in vacuum pressure, electricity, thermo, and mechanics. And they're going to come in sort of organized groups following these various laws, and hopefully that will be somewhat apparent as we go along. I think I have it in the wrong order, though. They'll let me know. Once again, it's Tege and Neil who do all the work, so I'll be leaving momentarily to sit with Warren. If, for some reason, you want more information about any of these demonstration experiments, there are pictures and further explanations on our homepage. So you can write down those numbers or call if you want to write down the phone number and ask us about it. Okay, without further ado.
Oh, stop. You make me blush. Now, ladies and gentlemen, boys and girls, children of all ages, Welcome to the greatest physics show on earth. Dun, 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 dun. Now, as previously mentioned, I'm Tege Margues. This is Neil Green. What we hope to do today is not only show you some fairly interesting physics principles, but we want to show you that physics is also fun, and it is the science of every day. It's not something as esoteric as you believe, listening to Einstein's theories and looking at Oppenheimer's work. We just want you to see that it's fun as well as functional. Now, one other thing.
Yeah, we also have some ground rules, right? For one thing, no mobbing the stage. Another thing.
We have security.
Yeah.
Amaris?
Maris right there is our security. Do not mob the stage. Second, if we were to screw up a demo, we will give you the sign like this, or if we do it correctly, but especially if we screw up, we will give you this sign, at which point you will say, ooh.
Deep, hearty, heartfelt, ooh.
And we will hand up our hands again and say, and you will say, ah.
Deep, sincere, soulful ah. Plus
Now,
we're very egocentric and we shatter easily.
we shall try this.
Beautiful. Yes.
Perfect. Now we are ready to begin.
Let's.
First off here, we have a regular old, what is it, champagne glass?
Is that Waterford or Kmart?
Now,
L.
I will drop
Bum, 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 bum.
said champagne glass.
Now. Oh no!
Now why did this happen? Why didn't it break? Well, you see here between the string and the pencil, there's frictional force, right? But why did the frictional force build up fast enough so that it didn't break, right? If you noticed, what happened first was that this swung down. But as this was swinging down, this started to drop, decreasing this radius here. Now, in order for, have you ever seen ice skaters when they held out their arms and they spin, and then they bring in their arms tighter and they spin a lot faster? The same thing was happening here. As we decreased the length here, it spun faster and faster and faster, saving my advisor champagne glass, and which is a good thing for my career.
Another analogy, if you will, is if anybody's ever swung a baseball bat, you know that by choking up on the bat or moving your grip up, the bat becomes easier to swing and you swing it faster. Well, that's what happened there with the string. As the string moved in closer and closer to the pencil, it began to spin faster and faster and wound more around the pencil. And for each winding around the pencil, you get a specific amount of friction. And anybody who's had a bad rug burn is very familiar with friction. Right. So the friction increases and it becomes enough to stop the wine glass from hitting the ground and shattering.
Now, seeing as how we're on the subject of things that spin, let's play with this regular old bike wheel. Now then, I'm going to give Tege a good spin as he faces the audience.
Spin me.
Let's see what happens.
Oh yeah. Rolling, rolling, rolling.
What's going on here? What's this? What's this? Did we practice this? What is this?
Damn it, she's got a mind of her own, Cotton. She's coming apart. I can't hold her.
Now, the bike wheel here is acting like a gyroscope. Has anybody here ever played with a gyroscope? No? Well, this essentially is a gyroscope. You get trippy effects with this. Like, for instance, this one. Now, what's really happening is this thing has something associated with it called rotational momentum, right? This momentum has to be conserved. When Tege was sitting down there, the initial momentum was 0. When he took this and deflected it, Now he's changed momentum. But now the chair is sitting there like, man, I got to make it 0 again. So how's it do it? Now it kicks in the opposite direction in order to conserve. And in the end, because they're both turning in opposite directions, in the end, the momentum is 0.
Now, interesting physics trivia. If everybody's ever noticed a helicopter, there's always a rotor on the back of the helicopter. The rotor is there for the exact same reason as I spun around in the chair. Now, once you have the helicopter going and the rotary ring on the top begins to spin, what happens is to conserve angular momentum, the body of the helicopter has to begin to rotate in the opposite direction. So you put a prop on the back, a rotor on the back, to spin and push it in the opposite direction, and therefore you get stable, level flight.
Now then, here, Tege, play with this for a while.
Okay, Jenny.
Ooh there, easy tiger.
Ooh. All right. Here endeth our cool bike wheel demo. But now, ladies and gentlemen, I'd like your absolute attention right now. Tege Margues has put his life in the line several times during our demo shows and has died several times, just like Kenny on South Park. Do we have any South Park fans in the audience?
Park? Yeah!
Yeah.
My
Yeah.
impression of Cartman, real quick.
Well, that does sound pretty good. Beefcake! Beefcake!
Today, we're going to try a demo we have never, ever tried before. We've practically barely tested it, and we're not sure if it's going to work. We call it lovingly the
Pendulum of Death.
Laugh with me, laugh with me. This, ladies and...
If it doesn't work, don't call my mother.
Now then, we will need a member from the viewing audience. Someone fairly strong, and there we go, young man. There you go. Thanks. All right, I want you to stand right here with me. Now, your job is critical. You and I will be making sure, Tege, this doesn't topple over and kill some people in the audience. Hopefully, right? Now,
One more thing. I would like you to bear witness that this is actually a bowling ball. The bowling ball of death. In the laundry bag of death.
death. Oop.
Much like us, he has character.
I will now tie the laundry bag of death. Whoa. Next, we will put it on the hook of death.
Ooh.
Now I will adjust the chain of death. As I'm up here violating all of the safety rules of death.
That's good.
Now we're just wrapping the chain of death around the extension pole of death that's attached to the ladder of death, held down by the clamps of death. Are we playing this out too much? Yeah. Oh, never mind.
Okay. Amara, sing the circle of life.
Now then.
Cheer up. One test swing.
Hold on, Tage.
Support yonder ladder.
Aye. Now then, what's your name for me?
Jordan.
Okay, Jordan. Cup your hands over just like this. Like me. There you go. Okay, cool.
On the key.
Back it up. Back it up, Tage. Back it up. Too close to the table. Absolute silence, please. Does anybody know why Tage is still alive?
Why do I not look like a character?
And thank you so much.
Well, would anyone care to hazard a guess? You, sir. Brilliant! You, my man, are a budding physicist. Exactly. Now, when I lifted the bowling ball up to my face, in essence, I gave it some energy. Now, upon releasing the bowling ball, this energy was transformed into motion. Now, in physics, we say that energy cannot be created or destroyed. This is the founding precept of physics. It's our dogma. So, at best, what could happen if no energy is being created in this thing? The bowling ball would have to come back exactly to the same point at which it started, right in front of my face. But we have other forces acting. Forces like friction and wind resistance. Now, wind resistance acts just like friction, except through air. Now, all of these come together to take some of the energy away from the bowling ball as it's swinging, actually slowing it down some, so that each time it swings, it can never, ever come back to the same height it was released from. And therefore, as long as I don't move my head, which I was damn sure not going to do, I cannot be hit.
Now then, what we have here is a vacuum pump, right? Much like a vacuum at home, it sucks. It sucks air, it just sucks air. Sucks it in here, blows it out there.
Dude,
right?
it sucks.
There's a vacuum bell jar, even though it doesn't look like a bell. Hey, don't worry about that. Now, if we were, perchance, to stick regular old marshmallows in there, what do you think might happen?
They'll get smaller? Who else thinks they'll get smaller?
Smaller. Smaller. Over here, smaller, smaller. Over here, smaller. Over here, smaller, smaller. Here, say, oh, how many?
So to the American.
How many think it's going to stay exactly the same? How many people there think the vacuum pump's going to break and it's not going to work? What? What?
Gee, thanks for the confidence. Ew, stinky.
The camera may have to zoom in on this one. Let it rip. Grow. Grow.
Grow!
Ah!
Grow, my little homunculus!
Can everybody see it growing? All right, cut her.
Bravissimo.
Now, can everybody see the little marshmallows here? They've kind of died and shriveled up.
They're raisin mellows.
They're mellow jerky now. But still, they're edible. Marshmallow? Marshmallow?
Well, while Neil is playing the Marshmallow Fairy, let me try to explain what happened. Now, we have what we would call a sea of air just surrounding us. We're all inhaling it, we're all breathing it, and we pretty much think it's sitting here stagnant, just sort of around us. But if you were able to zoom in on the individual air molecules, you'd see that they're pretty excitable, and they're bouncing up and down all over the place. Now, you get these air molecules bouncing up and down all over the place. They strike surfaces, striking me, striking you, striking everything. Now, this hitting on the surfaces creates what we call pressure. Now, atmospheric pressure at sea level is 14.7 pounds per square inch. Yeah, definitely 14.7. Yeah, definitely. 14.7 pounds per square inch. Now, why don't we feel 14.7 pounds per square inch pushing on us? That's because internally we have another 14.7 pounds per square inch pushing outwards. Now, a marshmallow is nothing more than sugar whipped into a foam, which is air bubbles trapped in a liquid. Now, these air bubbles are at atmospheric pressure when it's made. When we remove the air from the vacuum chamber, the air pressure in there now becomes less. But the pressure inside the bubbles, inside the marshmallows, are still 14.7 pounds. So what they want to do is equilibrate so that they get the same pressure pushing down as pushing up. So what do the bubbles do to compensate? They expand. Hence, the bubbles expand, the marshmallow itself expands. Now, there comes a point when the marshmallow itself expands so much that the little bubbles pop, and it shrinks down some. And then when we put the air back into the chamber, the pressure is now pushing on the marshmallow. Air pressure is pushing on the marshmallow. And the marshmallow no longer has the capability to support air pressure at its original size. So it shrinks even further. Are we all feeling me, as we would say in the vernacular? Groovy.
Now then, Tege, who actually has a beard, so he actually shaves, will now do the next demo. I, blessed with no beard, never mind. It's very touchy. This is now just plain old shaving cream. Into a plain old beaker.
Beaker from the Muppets.
Here we go. What's going to happen? Ew. Did you ever run out of shaving cream? Here's a nifty trick.
Dun dun. Dun dun. Dun dun. Dun dun.
Ew. Now, while you guys weren't looking, I snuck a microwave in here and put water inside it. The water's now heating up. Now, why does something boil? Does anybody know? They move faster and faster and faster, and we give them enough energy, they escape, right? Now, the problem with them is that they're being pressed down by air pressure. But what happens if we help them out a little bit by taking away the air pressure that's there? Now look at this water here. This water is not boiling.
I said it boils quicker. That's very good. Good job.
Anybody here from Denver?
Demo, that's the kind of thing you like. Keep up the good work.
Here we go. Everybody got their eye on the little thingy there?
Hurry up, it's fogging up.
Oh. We're watching it. We're watching it. Watching it. Can we see it?
I probably can't see it in the back, but man, is she going?
Oh, she's really going.
Okay,
Oh,
we're sucking water into the back.
we are? What? Oh, get the vacuum!
And now, ladies and gentlemen, we've succeeded in making big mess.
Ah. Now then, let me clean this up and let Tege take you into the wonderful world of electricity.
Yeah,
Yeah.
wonderful world of electricity, that's it. Oh, by the way, side note, does anybody know how a straw works? Ye old common drinking straw. Yes, you, sir. Good point, you do drink out of it, but what happens is, you place the straw in your mouth, you actually increase the volume of your mouth by dropping your jaw. This drops the pressure so that the outside pressure pushing on the water actually forces it up into your mouth. In physics, we don't use terms like suck. We don't suck in physics. There's always pressure, there's always something pushing. I meant to put that there. It was for comedic effect. Thank you. Oh yeah, electricity. This, ladies and gentlemen, is a Van de Graaff generator. It creates Van de Graaffs. No. It actually, this is just a big rubber band sitting in here. Now, as the rubber band passes up through here, there's a comb with really sharp points pointing towards the rubber band. Now, as the rubber band passes, the comb actually rips electrons off the rubber band. Heep, hoop, heep, hoop. Sound effects always help. So, it rips the electrons off the rubber band. But electrons are antisocial, and they don't like to be in the same spot. They try to get as far away from each other as possible. So, what they do is, in order to space themselves away from each other as far as possible, they travel through the metal comb into this dome right here and spread out on the dome as far as possible. Ooh. Will we be doing the pie plates first?
Yes, we will.
Now I'd like to show you some physics magic. I will now use my physics telekinetic powers to levitate the pie plates. If you'll all help me out with the chant, llama, 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 llama. Say it with me. Llama, 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 llama. Llama, 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 llama.
Stand back. Whoa.
Oh dear. Excuse me, we're having magical difficulties. Every good magician needs a magic wand. Now, let's begin the magic.
Ah! Oh! Sorry, just kidding.
Llama, 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 llama. Llama, 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 llama.
Was it llama?
It was llama,
For this one?
as opposed to goat.
Okay.
Llama, 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 llama. Focus, damn you, you're not focusing. Rise, rise, fall.
Bless them, bless them.
They have been blessed by the magic physics wand. You. Take a couple off, take a couple off.
Get that.
Thank you.
Now then, all the little electrons are now spread out on there, right? Now if they get up and they start to move, it causes a current, right? Now if you have enough of them there, they'll build up something called a potential. And that potential is going to make an electric field, right? Now, if I bring myself close, there's going to be a potential difference between the sphere and me. Between the sphere and me, right? So there's going to be a big electric field between me and the sphere. Now, all the electrons basically see this electric field as a big running river that they can jump into, right? And when you get a strong enough electric field, the electrons will jump across the air and into me, which is what happened once or twice there. Not when I actually hit the switch, when I faked it, but once or twice there. You might have seen the little, that's when I was getting shocked by accident.
That was caused by involuntary muscle contraction.
Well done. Now then, as we said before, these electrons are incredibly antisocial. So what if we were to give them away, perhaps? They could get even further apart than this ball. First there, I'd like to thank Margues. Thank you. We found out shortly before the show that if Tege or I tried this, it wasn't going to work too good for some reason.
Say, mama, don't I know you from somewhere? What your name is, baby? Oh, your weave is coming loose there. You hold the wand. You hold the magic wand. Call this demo morning here.
Everybody look really closely. You see what's happening?
Come on, baby, light my fire. Try to set the night on fire. Come on, baby, light my fire. Don't encourage me, it won't stop. Ah, yes.
Can you see these hairs up top here? Just out of here, way up top? Sure. Back is it. Unfortunately, because of the clumpiosity, which is actually a physics quantity.
Clumpiosity is a technical term. We don't expect you all to know it.
Because of the clumpiosity of the hair, it's not spreading out all that well. Now then. What causes this is the electrons are bunching up and spreading out. Now what if I were to give them a path to ground, where they really like to go?
Woo! Woo! Look at them go.
Now, can we turn it off? All of them left and went to ground. I'm fine.
Whoa! She still needs some discharging.
Now then, I'm in for a little bit of induction. Now what is induction?
It's when they pull you into the army. I'm forever blowing bubbles.
It's a very dangerous
Pretty
demo.
bubbles in the air.
So dangerous, Tege and I are not doing it. We need a member from the audience. Preferably female. Preferably short. Now this is a highly dangerous bubble blower thingy.
You are familiar with bubble blowing technique. Okay.
Can we have your name to the microphone?
Krista.
Neil!
What?
The bubble monster's got your finger!
I gotta get.
This is the bubble wand. Here you go.
Okay, now,
For this demo, stay right about here.
it's very important that you don't get too close to the Van de Graaff. See that black spot on the carpet? That's the last kid who got too close to the Van de Graaff.
Now, just dip and blow it to Van de Graaff. Crank her up, Tege.
She's cranked!
Beefcake! Beefcake!
Ooh.
What's going on here? Oh, oh.
Ooh.
Dip slow. Keep on dipping and blowing. Anybody see what's going on here? Just give us a second. For safety reasons, Tege is giving the Van de Graaff a better path than her to ground by putting the discharge sphere between us. Otherwise, it may just see her and say, hey, we can go to ground through her and jump across. Now, let me give it a shot. I'll move a little bit closer and Tege will take away the protective wand. Can you see how some bubbles are coming closer and some are moving apart? Away? Ah.
We're about to lose the Van de Graaff.
Good Lord, we're about to lose the Van de Graaff.
I think we should stop this demo here.
Yeah, cut her off, cut her off. Woo. Now, for those of you who caught it, what was happening was that because there was a huge negative charge in the Van de Graaff, all the little negative charges, which are free to move in the bubble, ran away from it. So if you can imagine a spaceship, all the negative charges, all the positive charges are hanging together in pairs, in couples, because that's the way they like to do it. But the problem is that all the positive charges are nailed to their seats. All the negative charges can walk up and down the aisle, annoying people. Now then, when they see the huge negative charge, all the negative charges that are on the spaceship, the bubble, run to the back of the spaceship to keep away from it. So now you have all the negative charge at one end of the spaceship, but now that leaves all the positive charge in the front of it. And the positive charge is the negative charge, and they attract. Some of them. And then the others, they get so close that they get some negative charge, and they get negative and positive. We have what?
Continue.
Whoa. And then they all jump off. Sorry. Cool.
We're missing my lightsaber.
Yes, we are. Hold on, where'd Tege go? Ah, there we go. Okay. Someone get Tege. Now then.
Lights, please.
Lights, please. Lights, please. Take a good look at the magic wand.
Luke,
Yes?
I am your father.
You're so silly.
Join me in the dark side. We will rule together. Luke?
Yes?
Pass the primatine mist. Thank you, and may the Force be with you.
Cool.
Coolness.
Now, the lightsaber effect can also be achieved.
Ooh, secondary lightsaber effect.
With this little...
Time constraints. We'll bypass this.
No, it's a quick one.
Should we do it? Should we go for it? Go for it. We've just been given the okay to go for the secondary lightsaber. Yeah. Woo! All right.
Keep the lights down.
Ooh, ooh. Ooh, ooh. Ooh, ooh. Come on, ride the train. Choo, choo, riding. Do.
Lights up, lights up. Now, lights up.
Well, I will now venture into explanations as he does the last one. Now, we've already established that the Van de Graaff machine has a whole lot of excess charge sitting on the surface. Now, fluorescent bulbs, which I'm sure we're all familiar with, have gas inside this tube. Now, apart from being antisocial, electrons are also rude. So what happens in their attempt to get to ground, when I bring the fluorescent bulb close to the Van de Graaff, the electrons actually jump into these 2 points here, through the bulb, travel to my hand, and therefore find an exit or a way to become neutral once again. Now, when this happens, as they're moving through the gas, they push and shove the atoms of the gas in there, in turn exciting the electrons that are in the gas. Now, when an electron gets excited, he picks up energy. When he relaxes again, he releases this energy. And when it's released, we see it in the form of light. Now, with the lightning ball, plasma orb, laser orb, I'm sure you're all familiar with. Yeah, I was just going by all the familiar names. What it actually does is it sets up an electric field, which doesn't actually work with the electrons themselves, but just sort of attracts them, like two magnets would attract one another. And they, in essence, directly excite the electrons inside the bulb, inside the gas. Now the field, because I'm at a different strength, as it were, than the orb in my electric field lines travel between me and the orb. And they're excited along these lines, so that any electrons between me and the orb will become excited and therefore emit a light.
This machine here, called a Wimshurst machine,
Is moving death.
basically. But that's why I'm going to use it. There we go. Lights down, please. Oh, Lordy. Oh, Mama. Oh, Mama. Oh, ah!
He lives! He lives! I have created a monster!
We get the same effect happening with the Wimshurst machine. Cool. Lights up.
Now, this is a dust explosion.
I would like to note that Tege is wearing safety goggles. So will I.
I have here regular old coffee mate, a substance which defies even modern science. Nobody knows what it's really made of. Ooh. Ah. Well, actually, let's try this first. Can't we burn it on the table, can I? Steve would have a fit.
Yeah.
Okay. Are we
Hold
ready?
on. Do you want to drop the lights or not?
Drop the lights. Okay, dim the lights for dramatic effect. Start the smoke machines. Oh, we don't have smoke machines. Never mind.
Wugga, 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 wugga.
Ooh. Ooh. Now,
Take the explanation.
who can tell me what 3 things you need in order to have a fire? Yeah, well, oh, go ahead. Oxygen, fuel, ignition, right. Good job. So, if we just have regular old coffee mate, just sitting here on the table and I put this flame to it, it's not gonna burn because the coffee mate isn't mixed with oxygen. It's just sitting there in a pile. But when I blow into the coffee mate, I, in effect, mix it with air. And as it approaches the open flame, we have our source of ignition. So we get it rapidly burning. We get a big blaze, a big poof. Now, Neil will carry on this demo using lycopodium powder instead of coffee mate, because it's lycopodium, only not quite.
Can't see? Who can't see?
Woo! Woo, child!
Again.
Now, for those of you interested, lycopodium is just the spore of the lycopodium moss. It's nothing particularly amazing or special in its properties. It's just that it's a really fine powder, and therefore we get it mixed more. Well, we get it mixed better with the air.
Wait till lights go.
Lights on, lights off. Come on.
Clap on, clap on, clap on, clap off. The clapper. Woo, child. Now, for our final
We're finally demo.
demo.
I would like to make just a brief note 21 years old. Why does anybody care?
This, ladies and gentlemen, is 200 proof ethyl alcohol, much like the kind you drink in liquor. Only the best hard liquor you can get is around 90 proof. This is 200 proof. This is one of our happier demos.
You got a chaser?
I need a chaser.
Hold this for a
Water,
minute.
please. Ah, thank you. Thank you very much. Okay. Once again, do not try this at home, even if you are 21. By the way, Neil, you'll be driving home tonight.
Okay, as home today. How dry I am. Nobody knows how dry I am.
You're flat.
You're drunk. Hey, you swallowing that? Now, when Tege blows it out, it atomizes the ethyl. And that means that it breaks it up into small particles, which again, mix with the oxygen really well, so that it can burn very readily. Now, to wrap up our demo show, we're going to introduce you to the very interesting world of pressure.
Pressure!
Tege, front and center. Front and center, and lose the mask. Front and center. Has anybody here ever watched Ninja Scroll?
Now, Neil will translate as I define pressure. Hikone no sokoi, iso na boshi, hikone so, hippon.
Hi,
Konnichiwa,
this is a sword.
a senator.
A sharp sword.
He,
Heat, heat.
Epone, sene, konishone ojai, isone o, iskone so deshiwai.
A sword is able to cut through things because at the very edge, there is a very high pressure. Because there's a low area.
Hai. Hai.
Translate. Oh.
Hai. Hai. Hai.
Let's see the sword again. Now, if we look along this edge here, we see a very small area, which magnifies the force. And this, when we hack it at someone, say, head, magnifies the force so much that we can separate the flesh and cut their head off. Now we're going to demonstrate this, but okay, well, just kidding, ladies and gentlemen. Just kidding, joke. All right, now, that was just regular pressure. Now let's see what air pressure does. Stage one explain on the other side of the stage so he's not drowned out.
Now then, this is called the Bernoulli effect. Oh, great. You've killed the pie plate of science. Now, anybody familiar with how an airplane wing works? Yeah, you back there reaching. Let's hear it.
It works because the top area is curved and that creates lower pressure.
You're brilliant. Exactly. Now, nature hates a vacuum, right? So the wing is moving through air. Hey, let's take it to the chalkboard of science. Here is a cross-section of our wing, typically known as an airfoil. Now, as it's moving through the air in this direction, air must travel over the wing as well as under the wing. But they have to meet back here at this point. Harder, it's not moving. Harder. Now, air must meet at this point at the same time. If not, there'll be a vacuum created back here. Now, if you'll notice, the curved distance is much longer than the flat distance, which means the air up here has to move faster. Now, faster moving air has a lower pressure, so that the air moving slowly down here actually pushes up on the wing and creates it to fly. Now, with the ball, what happens is the leaf blower creates a steady... Okay, the leaf blower creates a steady stream of air, right? The air comes up and does this around the ball. Now what happens is you have fast-moving air sitting around the ball, but this air out here is stagnant, standing still. So what happens is the stagnant air actually pushes on the ball from all directions, in essence, holding it locked in space.
Tege will now attempt to lie on the bed of nails. Absolute silence, please.
I will need you all to chant so that I may focus. I chi. Chant with me. Mama say, Mama sa, Mama maku sa. Mama say, Mama sa, Mama maku sa. Mama say, Mama sa, Mama maku sa. Come on, chant. My life depends on it.
Mama say,
Mama sa, Mama maku sa.
Chant, chant.
don't say
Mama sa, Mama maku sa.
Let's hear it for Tege.
Explain away. You grab the balloon.
Now, pressure is just a force over an area. Now, if you look at a single nail, it's tapered to a very fine point, so that when you strike it on the back, you apply force to it, but the force is concentrated onto a very small area. Now, when you have 3,600 nails, you have 3,600 times the area. Therefore, the same amount of force is now divided 3,600 times. So a nail that was once capable of piercing flesh, now that its pressure is divided by 3,600, it's easy to lie on it without doing damage. And hopefully this will prove it.
Bananananananana. Bun, banananananana. Bun, bananana. Hey! 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 Bun, bananananana. Bun, bun, bun. Shh, shh. Absolute silence. Let's hear it for Tege. March the light!
too. But that left an impression on me. But ching, yeah.
And here, ladies and gentlemen, concludes our demo show. Thank you very much for coming.
Bye, safe trip home.
If anyone has any questions or would like to talk to these guys, feel free to come on down.